Hi guys, Matt here. Today we'll be talking to you guys about the second shortest path algorithm we'll be doing. That's new Bellman Ford. Without further ado, I'll pass to myself and I'll go a little bit more in depth about this. Thanks.
Thanks for passing it back to me, Matt. I'm Matt. Welcome. And we're going to talk about Bellman Ford in a little bit more depth now. So, what is Bellman Ford? It's going to be the shortest path finding using relaxation. So, what that means is basically, unlike Dijkstra, which has a greedy approach of picking the shortest path at each turn, it's really going to figure out the shortest path to each node in the entire graph from your start node and then connect the dots through that. The main reason this is really important is it can be used for negative values. If you see here, I've run n minus 1 times, so that means it can be run n, where n is the number of nodes you have, minus 1 times in the graph. Because of this, unlike Dijkstra's, which gets caught in like negative feedback loops, which means it goes on forever, it can be used for negative values because it has a set cutoff point after a certain amount of running. It's also a dynamic approach, which we haven't talked much about dynamic versus other algorithms. But dynamic algorithms effectively just means it's going to be using space alongside its time complexity. Algorithms like Dijkstra's only need to keep a handful of variables, and the actual important thing is that the variable number is static. So if you're running a Dijkstra's on a graph of 2 nodes or a graph of 100 nodes, you're still only going to need those handful of variables, whereas with Bellman Ford, the amount of space is going to increase as the size of the graph increases. Now this comes into here. So why is Dijkstra so much more popular? So the reason I'm telling you about Bellman Ford here today, and honestly what it might have sounded like in the previous slide, is that Bellman Ford just does Dijkstra's but better. And yes and no. So it does have the ability to do negative loops. However, the number one reason we use Dijkstra's way more than Bellman Ford is the real world doesn't really fit the niche or the extra costs of running Bellman Ford compared to Dijkstra's. So typically these pathfinding algorithms might be used for the distance between two objects or two locations, Google Maps, that kind of stuff. And if you really think about it, it's impossible to have like a negative loop that constantly goes down if you're doing like map searching or pathfinding. So a lot of the times, if you're talking about costs or anything like that, yeah, there may be things that make it cheaper or you go closer to your distance, further away, but there's never going to be something that infinitely spirals down. Now, the reason that's really important is because unlike Dijkstra's, Bellman Ford has two major downsides to it. So space complexity, as I explained before, it actually has a lot more space required, and the time complexity. Now, it's okay to tune out a little bit for this. You might not 100% get it yet. We should cover time complexity pretty soon, and when you do, I'd really recommend coming back and just listening to this explanation. So the time complexity for Bellman Ford is worst case, it's going to be the number of vertices times the number of edges. Now, this is compared to Dijkstra's, which is the number of vertices squared. When we look at time complexity, for first, this may seem a little bit odd that I'm saying this is worse than this. And that's because normally if you have something times something, it's not considered worse compared to the polynomial squares. However, if you think about it with a graph, realistically, the number of edges, if it's connected, are either going to be equal to or more than the number of nodes. Because of this, it's typically going to be v times a higher number than v, let's say like v plus 5, for instance, as opposed to v, which is squared, is just v times v. So that's the reason why, even though it may not look like it, it is actually a worse time complexity algorithm. Again, totally fine if you do not understand this whatsoever. When you see time complexity, I'd recommend just coming back, having a little check at it. It's really important you do understand this kind of stuff. Now, pseudocode. This is on your canvas, so if you really need to check it, I'm pretty sure it's like week 7 of unit 3. Basically, firstly, this is the part that requires the space complexity. This is where we're initializing our storage of the graph, where we're setting all the distances besides our source node to infinite. So because of this, it'll work in the next one where we're relaxing it. So obviously, from 1 to the size number of vertices minus 1, basically, we're checking if the current distance is higher than the sum of two distances between it. So the current weight of the edge plus its predecessor, a node that's attached to that edge. This is why it's important to set for infinite, because obviously in the first rotation, it'll effectively sort most of the graph out. Again, we'll get to a demonstration in a bit. It can be a little bit hard to understand this. Basically, it's just going through and figuring out the shortest distance. This is the really important part. So because this runs not until like Dijkstra's where it's found the node, but for this set number of times. Um, Basically, you can check if there's going to be any negative feedback loops. If you do one last iteration after this n minus one, because at the end of this one, n minus one, there is also the proof online, I recommend looking at it, we can confirm that we will have the shortest path to every node. So if one decreases again, it means it's going to be a negative weight cycle. I'll put another demonstration in the demonstration in a sec. It's just that is the important part that lets it figure out those negative weight cycles. Otherwise, it just returns the distances. Beautiful. So we're going to do an example. So hopefully you guys watched my depth first search video. If you didn't, you're going to miss out on some lore. So Georgia has now found the brain of the sea from the last video, but on a way to deliver it to its owner, she found herself chased through the streets. We can say there's some, old school European city. The thief's with quite a fast car, but thankfully on her motorbike, she can navigate the smaller back streets faster than them. So we're going to draw a graph showing the paths she can take, with the positive weighted edges being how much the thieves can catch up and negative ones being time distance gained. Given she has a head start of 5, we can use Bellman Ford to figure out if she can deliver it safely in time. So here is going to be our graph. It's a little ugly, you're going to have to apologize. I'm going to have to apologize for that one, but it is what it is. Now, obviously I've done this one to show that basically our final path from start to goal is going to need to be less than 5. And obviously, you might already be able to see the path she needs to take. However, we'll use Bellman Ford considering this might have been, a massive map of the entire of London. So let's do our first relaxation. Basically, we start at 1. So we're going to start our start node. We go to all its edges. We go, hey, it's got an edge to B. Is that going to be less than infinity? Yes, 1 is less than infinity. So we'll fill that in. We'll do another step now. So we'll go from B. Is the value of the B in this table plus this edge here, so -2, less than infinity? Yep, it's -1. Same here with D, it's like that. Now, this is going to be the full first relaxation, so going through every single node. Basically, we're going to see this table has sort of already fixed itself out. So we don't need to worry about it too much more. Obviously, we want to do all the other relaxations as well. But you're going to find out that we've got a lovely path through here, 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 here. Now, the important thing is also that it's not going to tell you the path. It's just going to say the distance. So we do know now there is a distance from start to goal with a value of 3. Now, I've purposely included this here. It's a lovely little negative feedback loop. It's going to constantly go down. So let's say we've done our v-1 checks. Let's look for infinite loops. Pretend we have done our n-1 runs. Now if we do this again, so we go through all these little nodes, we go, yep, nothing decreases here. These are all the shortest paths. However, D to F, they're going to go down by 1 because -3 and then 2 is always going to go down by 1. So what you can do is you can then label in your table, these are negative infinite. The only concern with that is that, let's say goal was connected to F, it would also label goal as negative infinite. So sometimes you can, in this case, for instance, just label them as negative infinity and throw them out. Sometimes it's going to ruin your entire data. You're really not going to know. So that's why I'm actually going to follow up here with the conclusion. So firstly, I'd really recommend trying this in SnapApps, Edgy, or Python. Really give it a shot. Again, you're going to be using Dijkstra's more, but it's really handy to have this on table. The other thing is, while I can't give you guys homework, I do have a little thought experiment for you guys. How do you think you can fix the negative loop problem? Now, I'm put this here with feel free to make assumptions, because it's going to be really important that you do make assumptions in order to fix this. So maybe one of your key assumptions is, sorry, my cat's getting in the way. Maybe one of your key assumptions is that there's going to be no nodes with loops to themselves. For instance, imagine if F had a -1 value to itself, where it could infinitely go down. You may be able to somehow edit this graph, have more knowledge about all the graphs and edges in all the nodes and edges in your graph. But again, not essential, but I really recommend have a little think about how you could try and tackle not just being able to find negative loops, but perhaps returning a graph without negative loops and with the shortest path to the goal. Yeah, I'll pass back to myself for a little outro. Hope you've learned a lot.
Well, guys, thanks for watching. I really hope you enjoyed it. Again, some of the stuff covered here might seem a little bit more advanced than what you're expecting. I really recommend once you've covered more of those time complexity concepts just to come back and check this video out again. Thanks guys.